Hello, everybody. It was a little hurried, so I'm sorry for that. I'm Monica Beckwith, and I'm very thankful that you guys are here. I hope I can live up to the expectation of this big crowd. This is one of my favorite presentations because I get to talk about performance, which is what I do, performance engineering, and then I get to show how I apply it. So here we are. I call it the Java Performance Engineer Survival Guide. You could just call it some Performance Engineer Survival Guide, because most of the notes are applicable to anybody doing performance engineering. All right. So a little bit about me. As you probably know, I do Java performance engineering, which also means that most of the time I'm dealing with JVM and garbage collection issues, or trying to tune them. What is also interesting is kind of the background that I have is, so I have optimized JIT compilers, I've optimized JVM heuristics, I worked with garbage collectors, trying to optimize reclamation as well as allocation paths. So I was kind of lucky enough to work for companies like Advanced Micro Devices and then Sun Microsystems and eventually Oracle. And my last title at Oracle was First Garbage Collector Performance Lead. And now I'm independent, so I do solve a lot of managed runtime issues. So anything that runs over the JVM, I help solve any performance issues that they may encounter. The agenda is very simple. I'll talk about performance engineering, and I'll talk about how I specifically do Java performance analysis. And there are two things to it: the approach and the methodology. So with just knowing the approach and the methodology, what we're going to do is we're going to go have some fun, try to apply and build a problem statement and try to see how we can do performance analysis. So what is performance engineering? We all know that we have, but you start your performance engineering based on some performance requirements. If you don't have performance requirements, you make requirements, your non-functional requirements. And there's also the test. The performance test is a big part of performance engineering. Now, the other part of it, so now you have requirements and you have your test, there's something called performance analysis, because basically you need to reach your performance. So you try to figure out what are the holding points to be able to achieve the performance that you have. So there are two aspects of performance engineering. So let's look more at performance requirements. So first thing is, like I said, if you're not already given a set of requirements, how do you start? You start by asking questions. So the first thing is, what makes the user happy? The next is, what makes them unhappy? What makes them sad? And most often than not, if you are a performance engineer and somebody is contacting you, they already have some current issues that they're facing. So try to figure out what issues they have currently, what's on the top of their list, and their eventual goals, right? So then what do? We define and understand. So basically you try to understand the quality of service, because we're trying to build this requirement which may seem to be out of thin air, but it's not really that way, because every application, every service has something known as quality of service. So what is the quality of service? Try to understand that. And then you have to define this quality of service in terms of success metrics. So, and these success metrics should be measurable. That's the most important thing about performance engineering. You should be able to measure, analyze, and remeasure, reanalyze. So you should be able to define success metrics in measurable terms. So now these success metrics that you can measure, these are called your service level agreements. So for performance engineering, to be able to have performance requirements, you need service level agreements. So, for example, the absolute, so if there's a heartbeat and somebody else is, and there are multiple servers relying on heartbeats. So what's the absolute maximum latency that this distributed system can tolerate? 1 second, 5 seconds? So you need to be able to know that, and you need to be able to measure it either as well, and those are called your service level agreements. And then you define success, right? We already know what makes them happy, so you try to define success in terms, again, in terms of measurable terms. So the way you do it, you document, understand, and prioritize your SLAs. So we have our system level agreements, and we have documented them, but we need to sit down and figure out which one has top priority. So usually you would have heard something like throughput, latency, and footprint. You know, you can only achieve 2 out of 3. You cannot get all of them together. So that's the reason why we need to prioritize. Is latency more important to you than throughput? So by latency, I mean responsiveness. Is that more important than throughput? So then responsiveness comes first, then throughput, and then footprint. Okay, so I think that's what it's talking about. There are other things, you know, sometimes, you know, they come and talk about how many users the system can tolerate at max load, or sustainability of users. So that's called capacity planning. And then sometimes, you know, people who are hardware vendors, they may also want to know about CPU utilization and other such CPU-related metrics, because they can feed it back to the next generation of processors and other hardware compatible like environment. So then after we have defined success, we work for it. So you monitor, measure, and define performance in terms of throughput, latency, capacity, footprint, utilization. So basically your system level agreements that you have defined. So you have to be able to monitor, measure, and then that's how you do performance analysis. So let's do defining success. So we have, like I mentioned, we have system level agreements, and these are the agreements that I told you about. There's something called availability, but I'm not going to cover that right now. But that could be also in a highly available environment of distributed systems. Availability would be something that you would be measuring as well. But there are other factors to it, so so I'm not covering that right now. So let's start with throughput. So when you're trying to figure out how to measure or how to put it down in numbers, the first thing you want to know is what is the expected throughput. So your distributed system, what's the expected throughput of the distributed system? Can you fall below the expected throughput? Okay? And if you can, how long can you stay there? So these are all things that you should be able to measure, and these are all things that you should be able to quantify. So expected throughput, can you fall below expected, and how long can you stay there? And what's the lowest bar? You know, everybody will have a low bar. I mean, and you need to be able to measure that, because many a times you'll find yourself, your throughput could be fluctuating based on various different inputs. So you have to make sure that when you're doing performance tuning, you're able to keep your max and min and kind of stay in that range, right? So the next aspect is measurement. Where is throughput measured? And how is it measured? So first of all, how? So is it measured transactions per second, messages per second, or all of them? You know, whatever measurement metrics you have, you need to know them all. So like I said, where is it measured? So it's client side, server side, browser, or again, everywhere. So whatever information you can get, whatever information you can tune, that's what a performance engineer needs to gather. Let's talk about response time, and you'll see the similarity. When I go to the next one, you'll see the same, I'm asking the same questions. Expected response time, can you go above the expected? So basically, your responsiveness is decreasing. How long can you be in the decreased responsiveness state? And how much? What's that bar? How much can you exceed? And then similarly, response time measurements. How is it measured? So this is a whole talk by itself. Measuring responsiveness is really important, and having the right metrics is really important as well. Many a times people talk about average response time, which is ART in their lingo, and that's just not acceptable. What you need to know is how many times your system was not responsive. It doesn't matter how many times you were able to serve the users, but that one user that you couldn't serve in your because of some other issues, that is the thing that you want to know. To be able to design a successful performance system, you need to be able to capture that one time that you lost a user. So you need to know your max, which is the worst case. It's called worst case latency or worst case responsiveness. Where is it measured again? Client side, server side, complete loop. So it will be same for footprint. And then capacity management. The only reason I have mentioned capacity management now is because of the next bullet right here. So one of the things about capacity management, which is kind of different, is what happens if one system gets loaded more than the other. So it's a load balancing issue. So things that you may not care about in throughput because you're thinking about the entire system, so, and latency also, you're looking at everything and you're trying to find the worst case. But with capacity, you need to figure out individually. So in your distributed environment, you need to find out individual load balancing issues. And everything else is, like I said, similar. With capacity management, you're looking at the load again. So what's the maximum load that a system, like an individual system, and all the systems together can tolerate? How long they can stay on the maximum load? So basically, that's where I'm talking about when one system may fall over or fail over. So you need to know all those. So I'm not going to go into details of that, but something to keep in mind. What metrics are being captured also is very important with capacity management, because the more information you have, the more you can analyze and suggest applicable tuning measures. So now that we have the requirements, let's move on to performance analysis. And more specifically, Java performance analysis. Because the reason I'm talking about Java is because I can tell you certain tools that work with Java. And, so I'm kind of trying to keep it more specific to Java. So performance analysis, for that, you need to analyze what factors enable the end user experience to meet or exceed the promised quality of service. So it seems like a big sentence, but what we're trying to do is make your end user happy. There is a quality of service that every system promises the end users, and we're trying to make sure that we're going to meet or exceed the quality of service. It's as simple as that. So bottom line is we're tracking our SLAs, because remember, we just defined our requirements and we defined our system level agreements. So we're just trying to track it and try to keep them in the ranges that we put in the requirements. So let's look at the Java application. This is very simplified stack, application stack. And the reason it's simplified is because, like I said, you could apply it to any other application stack. So we start with the Java application itself, and then there's the application ecosystem, all right? Then the next layer down is where the application is running. It's running on a Java virtual machine. What we all know it as is a Java runtime environment, which is called the JRE. So when you download the runtime environment from Oracle or OpenJDK, that's what you're getting. You're getting an environment that your Java application can run on. It could run in now the whole thing could be in a virtual environment on cloud or wherever, but eventually it'll have a hardware somewhere. You'll have hardware somewhere, and so that's like I said, simplified stack. So when you're trying to do applications, so what I'm trying to do is like trying to take one layer at a time and tell you the tools that are available. So for application performance analysis, we try to track the application services. You need to know what services your application is offering. So, and then where the application servers, you want to track your application servers utilization and other system level agreements. If there's a database, you want to get information about the database as well, and similarly, any other services in the ecosystem, right? What about the JVM JRE? So there could be many. So what I'm trying to list here are the things that you would want to track. Sometimes the issues come in and they somehow know the problem, and and you could definitely start with that, but eventually just don't pigeonhole yourself into thinking that, oh, it's a garbage collection issue, because everybody comes over and says it's a garbage collection issue, and many times it's not a garbage collection issue. So my point being that you could have issues in all these other things. So try to know how to gather class loading stats, JIT compilation. Try to figure out how to, print compilation is the simplest one. Garbage collection stats, of course, print GC details, print GC timestamps, very important. Thread stats, locking stats, of course. And then OS level, you have system, the kernel stats, you have locking stats, of course, thread stats, so on and so forth. What I'm trying to show is that every layer, there's so much of information that you need to know, and don't just think of it being always this one thing. It's not just memory utilization, it's not just CPU utilization. There are many other things that could be a part of the performance problem, and they could be contributing to a bigger issue somewhere else. So that's why visualizing it as layers, you can actually figure out how and do the step-by-step approach. So at the hardware level, you could have memory bandwidth, which is also known as traffic, memory traffic, which is the physical memory, your DRAMs, consumption. So if you have multi-node system, some may be consuming more of the memory than the other nodes. So kind of, again, a load balancing issue at the lowest level. CPU core utilization. CPUs have multiple cores. They may not be loaded equally. Other issues. And many times you won't have to deal with the hardware issues because when you're dealing as an application level performance person, you don't really have to go that deep. And I'll talk about the process, okay, the approach. But these are the things, if you do work for advanced micro devices or Intel or Spark on Spark systems, you would have to know all these things too. CPU caches are very important, the different levels, the different latencies. Any other architectural specific things that you may have for your special architecture, and I/O stats, of course. So now that we know we have all these things that we can capture, let's try to think what we're trying to do. What are we trying to achieve? We're trying to improve the application. So then we want to do something known as the top-down approach. For top-down approach, I'm just going to go back again. So it's basically simple. The same stack that you just saw, I just put an arrow next to it showing it's going from top to down. Okay? And the process is always the same. Step 1, you get to monitor your application. Step 2, profile your application. Step 3, analyze. And step 4, tune and apply. So you made some tunings, try to apply, and then repeat. So it's a rinse and repeat kind of thing. And eventually, when you meet or exceed your SLAs, that's when you're done. Okay? But what if you were trying to improve the platform? Like I said, you're working for a hardware vendor, and you're trying to help them improve their platform. So then there's a different approach. See, the arrow changed. So this is called the bottom-up approach. Basically, you start from the hardware, and then you try to see different, most of the things above the hardware would be something that would be necessary to know because you want to know and use the right tools. But other than that, you're not tuning anything in those layers. And again, the process is the same, like I mentioned: monitor, profile, analyze, tune, and apply until you meet your system level agreements. So let's look more at the top-down approach. So I like to call the top-down approach as I have the power, okay, to modify the code, right? Many times people don't understand that. People think, oh my gosh, I have to tune my application. That means I have to look at all these different things. But you can also modify your code, and that's all right because you have the power to do it, right? So what you would think with the same layers, you will think of anything under the application in the ecosystem as just the platform. So again, you just need to know that this is what my application is running on so that you can use the right tools. Other than that, you don't have to worry about anything below the application level because you are just doing application performance analysis. So what do you monitor? So now if we apply the process to our approach, what are we monitoring? So the thing that we're monitoring is called system under test. So you want to have your system under test statistics, so you want to monitor and plot them. Okay, so let's see if it's, can everybody see that? The first block is called tools, and then active and passive are the two other blocks. Okay, cool. So the steps in monitoring, and most of the people know this as application process monitoring, APMs, all right? And many of the APMs out there are classified either as active or passive. So when we have active monitoring tools, they're simply creating alerts. So they're always monitoring, they're active, and they're creating alerts to make sure that anytime you exceed your service level agreements, they're going to send an alert to you. So it's active 24 hours, and that's simply that. The second is called passive, which is basically like a snoop. These are network taps, and they just sit and monitor ever so often. So it's not active, it's called passive. I also like to call something called offline monitoring, which is basically just looking at your logs, all the logs every time. If you want to improve your system, you need to be able to capture logs and be able to access those logs later. So because I'm a performance engineer and that's what I do, I heavily rely, actually I do offline monitoring all the time. I heavily rely on logs. And that's, I look for patterns in logs and stuff like that, so it's really helpful for me. So what tools do we have? So we have something called Visual VM. If you have worked with Java, you definitely know Visual VM. And then there's now also Java Flight Recorder that is also available in the OpenJDK. So most of the tools that I've mentioned here are non-commercial tools. These are very helpful, and the most helpful ones are anything that says print before that. So print compilation, print GC details, print GC date stamps, and then for class loader stats, you want to look at the JMaps, and J commands. So these are the things that you would do for Java. Again, this is very specific to Java because I would have hundreds of slides if I took every other language there. So next is, because like I said, you need to know some things about your platform. For example, what if it's a Linux platform? You have lots of things that can tell you about the system, about your platform. So MP-stats, sys-stats, and all these other ones. There's something called CPU-Z, very useful to find out individual core utilizations, and cacti and all those things anyway. So these are good for distributed systems. So now that we know what we are monitoring and what tools we are using, we're going to move on to profile and analyze. And how can we do that, and why would we do that? Because we already have all the data we need. We are already monitoring these. We are already capturing logs. So now we can move on to profile and analyze. So now we can identify areas of improvement. We look at the logs. We have post processors for these logs, and then you identify areas of improvement. Once you identify areas of improvement, you want to profile for the hotspots. Now, profiling is very important because with profiling, you're trying to, so you have a hotspot, but then you don't know why is it hot. So profiling helps you understand why is that particular hotspot is hot. And then you analyze. So profiling and analysis go hand in hand, okay? So what tools do we have for profiling and analysis? Again, we have, I'm only talking about non-commercial ones. So Oracle Solaris Studio Performance Analyzer, or something like that. It used to be called Sun Studio Analyzer, very simple, but the name kept changing over time. But the tool is the most useful tool I have found ever. This is my trusted tool. I don't recommend many tools, but that's my most trusted tool. It's great for Java performance analysis. Of course, if you're dealing with static compilers, then it's really, that's what it started with. It started with C++ analysis. And then there's other tools. There's perf tools, PAPI. If you have a architecture specific, if you want to deep dive into the architecture specific things, then you have CodeXL. And then we have dtrace. People who are familiar with Solaris, they love dtrace, and OProfile is on Linux, and so on and so forth. For Java applications, I already mentioned Visual VM, but you also have something called NetBeans Profiler and JConsole. People have used JConsole from the beginning of times. So I don't want to, so people know JConsole, I'm pretty sure. Now comes tuning. So when we're dealing with Java application or anything, or managed runtime application, the first thing we want to do is tune the JVM and garbage collection. So I have a bunch of quick cheats here based on my experience. First thing you want to do is select the right heap, the right GC algorithm. Now, you may always say that, oh, I don't know which algorithm is different, but then there's a different talk for that. But trust me, each algorithm serves its purpose. You want to do latency-sensitive garbage collection. You want to be more sensitive to throughput, or you want to have a mix of both and be able to have a little finer control. So there are different GC algorithms for each of them. Most garbage collectors in OpenJDK hotspot are generational. What that means is that you have a young generation and an old generation. So that gives you an advantage of getting really good throughput. But because you have generations, you have to make use of them, right? And the way you make use of these generations is that you want to age your objects appropriately. Most of the application, most of the life of objects have a span, right? Some are long-lived, and then they could be static or transient, but they're long-lived. So you want to make sure that you're promoting them into the old generation. Some of them are short-lived, okay? Transaction types. You want to age them kind of like sieve. You pass these objects to a sieve, and then you try to promote only what's necessary. Yes, it's easier said than done, but that's what you have to do. That's what a GC tuning person will do anyway for you. So that's what I mentioned. Promote only long-lived objects. Something to know is, like I said, this is specific to GC algorithms that use stop-the-world threads. What are stop-the-world threads? Basically, your application threads will be brought to a safe point, and your garbage collection threads will do its collection work. Okay, it could include mark, sweep, compact, or marking could be distributed even further. But the point being that your garbage collection has stopped the world threads. So you want to, if your garbage collection has stopped the world threads, you want to make sure that you're doing lots of GC work per thread, okay? And then you want to account for, if you have different virtual machines running, Java virtual machines, you want to account for GC work per virtual machine as well. So kind of make sure that you are able to distribute your, by threads, I mean the CPU threads that can run on the CPU. So when your garbage collection needs to run, it's going to take over those threads, and you should be able to distribute them in an efficient manner. Some algorithms have concurrent work that's done during garbage collection, and same thing applies to them too. So you have concurrent threads, you make sure that you can account for them. And this goes into details of the virtual machine. There's something called compressed hoops. Make sure that's enabled and see if it can be helpful. Sometimes with JDK 8, you can go up to 64 or a little less than 64 gigs. Try to see if that's going to be helpful. Yes, it's going to change the alignment to 16 bytes instead of 8 bytes, but you know, there may be a slight advantage to using compressed hoops with 64 up to 64 gigs. So see if that helps. Larger heaps may need always pre-touch. If anybody has looked at the command line options, and you will see something called always pre-touch, and you'll be like, okay, it's been there for years. But the reason it's been there is because it pre-touches. So it's based on the first touch algorithm of your operating system, where your heap, the big heaps, will not be pushed up or swapped or something. So these things are important. Try to investigate these options if you get a chance. Use large pages is another very important option. And nowadays the CPUs have a lot of different page sizes, so you could investigate that as well. So then you could tune your code to meet or exceed your SLAs. So how do you do that? Make sure your code has appropriate ramp ups and ramp downs, object age and retention. See, the allocation is done by your code, right? So you are in control of it. Remember, you have the power to modify your code. So think about the object age and retention strategies and apply it to your code. Understand what forms your long-lived data set. And confirm you're measuring the right things. You know, if you're making a change, make sure that change is shown somewhere. Otherwise, you just go in a weird loop. What about bottom-up approach? Again, in the bottom-up case, I like to call it, I need the power. And you need the power to be able to stress the platform. What that means is that I have a new feature that I'm trying to test, or I'm trying to see how much the utilization I can push through. So you need to gather the power. You no longer have access to an application code. You may have to write your own benchmarks or write your own application. In the bottom-up approach, it's the same thing. The entire bottom half is more than half is your platform, right? So you're trying to stress the platform. So where do we start? Know what you're stressing, okay? Get the right appropriate workload and application. Get the appropriate tools, and we'll walk through an example. So if you're, these are just simple examples, but I'll actually go through a problem statement. So for CPU, you want to gather performance counter information for various things that are listed here right now. So you have core stats, cache misses, blah, blah, blah. And this is very important because we're doing the bottom-up approach. Remember, CPU is the main thing. So you want to make sure that you're stressing and gathering information on load store units and stuff like that, which is basically how your memory is accessed. For memory, you want to gather information based on utilization, bandwidth, read and write. So read and write ratios, how they impact. So, for example, we were testing a new memory, a RAM that could have huge capacity. But guess what? Its write bandwidth sucked. It was so bad that they were trying to hide it. So when people come out and they're trying to sell your product and they say, these are the bandwidths that we can support, and you can see like only 2% writes. I'm like, wow, 98% reads and only 2% write. What's going on? It's because the bandwidth sucked. So when they show you a workload, they do all these fancy things, but it's all actually just reading and not writing. So when you are that person trying to do these benchmarks, make sure you're not messing up. Make sure you're measuring writes and reads separately. Okay, cross traffic as well as important. What about the JVM and garbage collection? So if it's a new garbage collector that you're stressing or a new JVM feature that you're stressing, you need to gather information related to the change. Remember, it's a new feature. What has changed? So if it's a new GC, as in this example, you want to gather all this information. Figure out how many phases the garbage collection is going to have. Any parallel work queues, what's the performance for those? Concurrent work, again. Any internal queues or buffers that we need to know about, because these will help with the thresholds, and any GC work that's staged. So if it's a serial work, so you can only do this particular GC work after one work completes. You need to figure that out, because that will be your performance bottleneck, right? You can already visualize what is going to cause performance issues, right? So where do we go next? We did know what you're stressing. We were going to go get the writer tools, and then the application as well. Okay? So let's go have some fun. Let's build a problem statement. So for this particular thing, I chose something from OpenJDK 9, Java 9, which is called improvements in contended locking. So that's the problem statement. Improve the performance of contended Java object monitors. What's important here is the word contended. Because if you may know, prior to Java 9, there are lots of optimizations, especially one known as bias locking, that went in for uncontended locks. So whenever you have uncontended locks, you can use an optimization called bias locking. But we are specifically talking about contended lock. So let's first, now that we have a problem statement, let's first understand what are contended locks. So let's say you have a single thread T, which is executing a synchronized method. Okay? You have a synchronized method and it is single thread T executing it. It's very happy by itself. But then a different thread, U, wants to enter the synchronized method, which is already locked by T. Okay? Now this is contention. So if two or more threads want to modify an object and that's synchronized, then you have a contention. So contended locks. So what do we mean by contended? So now we know what is contention. Now let's say what we mean by contended locks. So contended locks are like heavyweight locks. They're also known as inflated locks. People who have worked with the operating system already know these terms. Basically, these are not thin locks. They are called fat locks or inflated locks or heavyweight locks. So your object monitor, so Java object monitor, maintains wait set. So because it's waiting for contention, so those threads will have to go and they're going to sit in the wait set. So if I had to draw something, this is what I came up with. So you have the object monitor, and then you have an queue when you enter. So you have an enter queue, and then you can exit the monitor. But because we have the wait set, and because there may be contention, all those threads will wait in the wait queue. So very simple. So what is a wait set? A set of threads, right? At creation, a wait set is empty because at creation, your lock is not contended, right? So the wait set is empty. And you can manipulate by object wait, object notify, and notify all. The reason I'm saying all these things because I'm going to measure, we're going to have to measure these things. We don't need to understand them right now, but if this was a problem statement, we'll have to go and understand all of them for sure, okay? So after understanding them, I decided that I know that notify needs to go that way and wait needs to go this way. So basically what I'm saying is that if you have a contention, you need to send the wait notification, and the thread goes and sits in the queue. And then once it's ready, you go and get notified, and then the thread moves to the enter queue. So remember, so now we have the problem statement, we understand the problem, and then we're going to apply the same things. So know what you're stressing. And for this particular JEP, I already knew what we were stressing because it's already mentioned in the JEP. And by the way, a JEP is a Java JDK enhancement proposal. So for OpenJDK, you can find multiple JEPs, enhancement proposals, and this was one of them. So usually a JEP will have these targets and everything specified, and this is what I took from that page. So they want the speed up targets were Java monitor enter operations, Java monitor exit operations, platform event unpark, and a couple of others. So let's just pick these three. And so the next step, so after I know what I'm stressing, I want to get the appropriate application or benchmark to stress it. So for this I used, and again, this was all listed on the page, so I picked up one of the benchmarks, which is by Doug Lee. It's called Lock Loops, and it was created for JSR 166. So it compares various other locking techniques, but we just need to stress contended locking. So basically, what is important to us is this particular thing. We want to make sure that we are testing synchronized this. So when we are looking at code, the generated code, we're going to look at this particular thing. And this is a very simple test, basically. So where to next? So remember I said ensure that you're in fact measuring what you think you're measuring. So in this particular case, even I fell for it. I thought I was measuring contended locking, but I didn't see any changes. And that was because I did not bypass bias locking, and I did not say use heavy monitors all the time. Because I'm stressing contended locks, I need to make sure, remember I said contended locks are heavy locks, fat locks, inflated locks. I need to make sure that that's what Java gives, the JVM gives me. It gives me a heavy monitor for it. So I have to ask for it right there. So every time I can consistently measure those contended locks, okay? So now the tool. So like I said, I think between the two slides that you saw previously and this one, I think the name changed again, so I'm sorry for not having consistent name. But it's now called Oracle Developer Studio Performance Tool. And depending on how much time we get, I will show you how the tool works. And I was going to go link to this tool too from here, but I'm not going to do that. Basically, what we do in this particular tool is we profile based on certain parameters. In my case, it's very simple. I'm doing time-based, so I'm going to just go with the defaults. And after profiling, we analyze it. So this particular tool provides an analyzer GUI as well as the collection tool, okay? Here are some of the options. It is automatically going to identify if it's a Java application. So JON is on by default. PON by default is about 100 samples per second. That's your clock profiling. You could do heap tracing with it. You could specify a duration, when to start and finish your collection. And you can do hardware counter profiling if you're doing profiling at the hardware level. And we're not doing any of those except for whatever the defaults are. So now let's talk about observing the targeted improvements. Okay? Remember these three things that I had identified, the speed up targets earlier? We're going to go visualize that. So this is supposed to be a demo, and I could go back to it after I change from the screen. So imagine you saw a demo right now, okay? And so now I'm going to summarize the results. So, so what did you see in that demo? What you saw was, let's say, what you saw was something about Java Monitor. The reason I don't want to inundate you with the demo is because you will see a bunch of things and bunch of method names and then code, and then you'll be all confused. And it's confusing for me too. It's not that we are any different. But, and then, so what I did is I went back and tried to understand what I'm doing, like what is all this code? So for Java Monitor enter operations, I went and looked at the code. So if the runtime says it's contended or inflated logs, it has two paths. It'll do two things. There'll be an object monitor enter, and there's something called object synchronizer slow enter, okay? And this was in, this was prior to Java 9. With Java 9, they added something called object synchronizer quick enter. Remember, they were trying to improve the time, the object enter, monitor enter time. So they added a new path called synchronizer quick enter, okay? So if I had shown you the demo, I would have dived into all of these things, and then you would see the slow enter right there. So what you're seeing over here is kind of like a call stack. So in the middle is what you're looking at, and then that on the top is the caller, and the bottom are the callees. Okay, so, and then what also you can see is a baseline and experiment 1. So what in this particular scenario, I compared two experiments, one taken with JDK 8 and one with JDK 9. And I compared them based on, like I said, time, right? If I had shown you the demo, I would have walked on by all of these things. But for now, you can go and try it too. So just go get that Douglas benchmark and try this particular thing. So, but what you would see is the time spent. You see, is only 7.715 seconds spent, because, and this is seconds because remember I have it in this big loop with so many threads and all those things. So I want to be able to measure it and measure it consistently. So I should be able to get these numbers every time I'm measuring. So I get 7.715 seconds for JDK 9 and 11.118 seconds for JDK 8. So these are the observations. So what you see here, your monitor enter time with, so the first column is JDK 9, exclusive time. Another thing with this is that you have exclusive and inclusive time. So exclusive time is basically just the time spent in your method. And if I have any other callees, then it'll be inclusive time from me down on. So when I show you inclusive time, it's basically anything I'm calling is included in my time, in my method. So I'm a method, anything I'm calling is included in my time, so it's inclusive. And if I'm a method, anything that I'm spending time on is exclusive to me. So the top is exclusive time, and then the bottom is inclusive time. So the time spent in object monitor enter, exclusive or inclusive, has improved for JDK 9 because they have a new the fast path. So this is what is new. So when you see 0, it's not that it was super fast, but that method didn't exist, right? So in JDK, remember I said this was not there. They introduced that in JDK 9. So you see that 9 seconds were spent in there. What about slow enter? That's what I showed you when I showed you the call stack. I showed you slow enter, and that was the inclusive time and exclusive time. Again, JDK 9 shows very a good amount of improvement. Similarly, I think I'm going to be out of time, but similarly for Java Monitor exit operations, you see that JDK 9 shows improvements, and then there's something called platform event Unpark. Again, top is exclusive, bottom is inclusive, and that's the event name. The method name is called OS Platform Event Unpark because that's what it's called eventually. There are different modes of visualization in the tool, in the analyzer tool. You can visualize these runtime methods. So then you can see that. So I think that's called machine level. There's an expert which kind of shows you the Java code as well as like assembly level code, which is your native code. And then there is something called user, which only shows you user level code. So again, if you have time and if you feel like it, please go try that tool out. That's my #1 go-to tool, and it's very helpful. Further reading, I had to read all these things. If you feel like reading it, please go ahead. If you're interested in reading about BIOS locking and hotspot, which is the Java virtual machine, then go to that link over there. There's a great Java performance book by Charlie Hunt and Binu John. If you're interested in Java performance at all, please read the book. Synchronization, if anybody is interested in reading about synchronization, there's a link for that. There is a link for the JLS spec. Go have fun. And of course the JEP that all this was based on is right there as well. So that concludes my presentation. I'm sorry I didn't have time for the demo, but I am open for questions, and maybe some other time if you guys just come by, I can show you how the tool works.
Hi, question. Do you know what were the actual improvements in this quick enter? It was the
so it's
operating system improvements, calling native methods, syscalls, or? Yeah,
so the runtime. So basically this is in the runtime. So the Java virtual machine has the garbage collector, the JIT compiler, which is the advanced optimizations, and then it has the runtime. So the runtime did this optimization where it can go this fast path. The slow enter does a lot of other things. So you can just...
Fast path means it doesn't answer the syscall, or?
Yeah, I mean, it doesn't... No, there's a lot of other monitor inflation and monitor checks that it has to do. In FastPath, it assumes them to be correct. So it's like yes and no. So it just takes yes for all these other assumptions. So it directly goes and does the fast path. And the slow path, it has to check every time for 3 different nodes.
Fall back to slow path.
Yes, of course, always. If your assumptions are, this is runtime. So if your assumptions are not correct, you fall back to the slow path. Okay, cool. Thank you.